This video is about properties of solids, liquids, and gases. The structure of solids, liquids, and gases is quite different. Solids are very compact and organized and have a fixed shape and a fixed volume. Liquids, on the other hand, start to flow past each other. They can take on the shape of their container. They don't just fill up any old volume. They'll have a set volume, a max volume, but they will take on and flow to the shape of their container. And gases have really high energy particles and constant rapid random motion. They'll fill up the whole shape and volume of their container. And so we got to talk a little bit about their properties and some of their attractive forces that are at play. So gases are really low density. Again, they're widely spread apart in constant, rapid, random motion. Liquids have higher density, and so do solids. Sometimes, they're not, they can be pretty similar in terms of densities. Sometimes the solids densities are just a little bit more dense, but it is a little bit substance dependent because there are times, for example, with water, its solid can actually be less dense than its liquid. So, in general, liquids and solids are higher density compared to gases. Gases do not have a defined shape. They take on the shape of their container. So do liquids, but they won't take on the volume of their container. So liquids have an undefined shape, but they do have a defined volume. 100 milliliters is 100 milliliters, but you can pour it into a tall, narrow cylinder, or you can pour it into a wide, stout beaker. So it has an indefinite shape, but it does have a defined volume. And solids have defined shapes and volumes. And all of this is really due to the relative strength of their attractive forces. How much are the particles attracted to each other? So gases have the weakest attractive forces. Their particles just really aren't very attracted to each other in the gas phase. And then liquids are in the middle for attractive forces, and solids have the strongest attractive forces between the particles, holding those particles in the solid state. So definite really means that property doesn't change when placed in a container. This is why, the solids have a definite volume, right? It doesn't matter what container, we put this cube in, it's going to have that same shape. Indefinite means it takes the shape or property of the container. So like liquids and gases are taking the shape of their container. Okay, so substances that have really strong forces of attraction will have high melting and boiling points. So ionic compounds have some of the strongest attraction and therefore have a really high melting and boiling point. So let's look at this example, this practice example. Based on the melting points of methane, ammonia, and water, which compound exhibits the strongest force of attraction between molecules, and which one exhibits the weakest force? So highest melting point is going to be strongest force. Well, 0 is higher than either of these negative numbers, so we're going to say strongest for water. And then an increasingly negative number is an even lower number. It might be helpful to label these high, and then this is your, medium, and then this is your lowest melting, your negative 182 degrees Celsius. So that's going to be your weakest force between the molecules, is going to be your very lowest boiling point. Now, the reason that these three molecules are important, methane, ammonia, and water, is that they all have relatively similar masses. So, these are, in terms of comparing molecules, we would say that these are, roughly similar mass molecules. They're not wildly different in terms of mass. And so it's a bit odd that water would have such a high melting point compared to methane. That methane's melting point is negative 182 degrees Celsius, or 182 degrees different than water, is a pretty big difference. And so we want to be able to explain that. So that's the next topic. Intermolecular forces attempt to explain these differences in properties for what otherwise seem like similar molecules.